Hello. Hello. Good morning. I'm Bhavani Thuraisingam. It's November 6th, around 5 o'clock in the morning, Central Daylight Time in the United States. And I'm giving this placeholder keynote presentation. And I will actually be giving this keynote presentation at IEEE's SmartCloud conference in about 3 hours from now. And so I always take a presentation just in case there is a technology glitch. So I'm going to give this presentation virtually at the IEEE SmartCloud conference. And again, thank you very much for inviting me to give this presentation. And I'm really honored to give this keynote presentation. And I'm Bhavani Thuraisingam from the University of Texas at Dallas. So now what I'm going to do is share my screen. Okay, so the title of my talk is Integrating Data Science and Cybersecurity with Applications in Cloud-Based Smart Internet of Things. So there are 4 parts: integrating cybersecurity and AI data science. So I'm using the words data science, artificial intelligence, and cybersecurity interchangeably. And so I will talk about big data security and privacy, privacy-aware quantified self, data science for cybersecurity applications, and what happens if the data science machine learning techniques are attacked. And so that's securing data science, and then trustworthy machine learning AI. Part 2 is security and privacy for Internet of Things. In particular, I'll be talking about Internet of Transportation and Infrastructures. And then part 3 is applying part 1 to part 2. So applications of security AI for smart world systems, smart things, smart Internet of Things, in particular, smart cities, in particular, Internet of Transportation and Infrastructures. And then finally, the role of the cloud. A number of sponsors have funded this work. And I would also like to thank my colleagues, Professors Alvaro Cardenas, Murad Kantajalu, Latifa Khan, and our former PhD student, Dr. Raul Quenenes, and our project coordinator, Ms. Rhonda Walls. So I'm just going to make sure that keeping the other machine on so that, I can keep an eye on the time, right? So I've been given 1 hour for this presentation. So there'll be questions and answers. So I'll try and limit my talk to about 45, 50 minutes. Okay, so security and AI, integrating cybersecurity and artificial intelligence, data science, machine learning. So the motivation, this is part 1, okay? So data mining, security, and privacy. So we know that with data mining, machine learning, you can put collections of public information or unclassified data together and infer something that is highly sensitive, highly private, okay? So the idea of integrating data mining, security, and privacy, I gave a keynote address at the IFIP Database Security Conference 11.3 in 1996 in Como, Italy, and then later Pacific Asia Knowledge Discovery and Database Conference in 1998 in Melbourne, Australia. And then I published what I call a landmark paper while at NSF in 2002. The reason I call it a landmark paper, it's just not that I want to brag, but when you're a program director at NSF and when you when you write a paper for CKDD, providing strategic directions, and of course everyone pays attention, and such a paper gets a lot of citations. And so it spawned a new area of research. I'm sure if I write that paper now, it wouldn't get as many citations. Okay, so then the IBM researchers, IBM's Rakesh Agarwal and his colleagues, they coined the term privacy-preserving data mining. So you have the original data, you add noise, then you have the noise-added data. You go through a modified data mining process with the noise-added data, but the final results have to be the same. So then when I joined UT Dallas in fall 2004, with my colleague, Dr. Murad Kantajulu, we supervised a joint PhD student, Dr. Li Liu. She was actually our first PhD student, and she focused on privacy preserving decision trees, and in particular, elaborated on the perturbation method. So when you mean noise added here, you either perturb the data or randomize the data. And so this work was carried out between 2000, latter part of 2004, actually, 2005, early part of 2008. And so much later, probably around 10 years later, data mining, security, and privacy, there was this big data, right? Exacerbated with big data and data science. And so I hosted a workshop, NSF workshop on big data security and privacy in September 2014, and presented the results to the Interagency Working Group in February 2015 in Washington, DC on data privacy. Okay, because now we've got big data, massive amounts of data, so you can collect data, analyze the data, and infer something that is highly sensitive or highly private. So what did we do at that workshop, right? What were the findings? So we said, due to the technological advances, right, big data security and privacy, so due to the technological advances and novel applications, it is now possible to capture, process, analyze large amounts of data for various tasks. It could be for healthcare, for COVID applications, or medicine, or finance, marketing, you name it, right? Manufacturing, transportation systems, including cybersecurity tasks like access control and so on, right? Or malware analysis. So for instance, security tasks could include user authentication, access control, anomaly detection, user monitoring, insider threat detection. So analyzing large amounts of data, and also data is collected on the web. You can make connections, relationships among individuals, and it could help with homeland protection, disease outbreaks, and so on. Collected data, even if you anonymize it, you can remove the identifiers, but when you link the records together, you could re-identify the individuals, right? You have two unclassified records, and then you put them together, and you could have a classified record, or you could identify, the privacy could be violated, identify the individuals. Security tasks such as authentication and access control, they could require detailed information about users, multi-factor authentication, and so on. So this information, right, if misused or stolen, it could lead to privacy breaches, right? So when you collect detailed information. So what were the directions? Securing the data, like access control models, privacy enhanced techniques, again, big data analytics, data science for cybersecurity, and also what happens if the machine learning techniques are attacked. So I'm not going to talk about access control models. Of course, for big data, you have different types of access control models for different types of data, and how do you integrate those models? So those were some of the things that aspects we discussed at the workshop. What I'm going to talk about, privacy enhanced stuff, techniques, data science for cybersecurity, and securing machine learning. Okay, so privacy aware quantified self. Sociologists, psychologists, they've come up with this whole notion of quantified self, right? You're carrying mobile users and smartphones, and so there are billions of users. So what they are saying is you can collect all the personal data and give advice to the user, the person, so that he or she can improve his health or personal life habits and so on. So for instance, I love vanilla ice cream and milk chocolates, right? And I don't keep any of it in the fridge, but suppose I do have them. Wouldn't it be great when I open the fridge and try to eat a vanilla ice cream, right? And then what happens? There is a message that is sent to my smartphone or my iPhone, and it says, no, you're not supposed to eat vanilla ice cream or drink vanilla ice cream or eat milk chocolates, right? But what happens if that information is shared with service providers like my insurance companies and so on? Right? Such data collection and sharing are often being carried out without the user's knowledge. On the one hand, it helps me, right, with my health and personal habits and so on. But if it's shared with my insurance company, it's going to be devastating, right? So for instance, data collected by device monitoring glucose, they could be used by insurance company to deny coverage, not just to me, but also to my son and my grandchildren, right? So such privacy violations could easily get out of control. If the data collectors could aggregate financial health related retweets and Facebook activities and purchase patterns and so on, there's just no privacy and there could be some damaging consequences. To address these growing challenges, we need tools. While quantified self movement that the sociologists and psychologists are coming up with is really good, but we need privacy for these quantified self applications. So you can see there's this Fitbit and what's this glucose monitoring. So all these devices are giving out information. So what we have done is come up with a privacy aware quantified self data management framework. And so there is in our smartphone, there's health data, fitness data, location, social media, image, other sources. And that's being used for data collection, data storage, data analytics, data sharing. Some of the data could be stored in the cloud, and some could be encrypted, and we can anonymize the data, and using cloud services, we can get the data. So we call this privacy aware quantified self manager. But how do we get privacy? What we are saying is policies have to govern every step of the way, right? So we have policy aware data collection, policy aware data storage, policy aware data analytics, policy aware data sharing. Okay, so that's what we are doing. And we need to come up with appropriate policies. And we computer scientists, we just come up sometimes with TOY policies. So we are working with policy experts, right, to those who really work with policies to come up with appropriate real world policies. Okay, so this is what, and to give you more information here, this is our smartphone, cloud-based encrypted data storage, right? So lots of data, so we have policy aware data collection, storage, access, analytics, learning, and sharing. Lots of data being collected, right? Some of the data would have to be stored in the cloud, some in the mobile device, some maybe you may want to use an edge. Based on access control policies, local apps running on the device will be given access to some of the collected data. When needed, these apps will be allowed to access some of the encrypted data stored in the cloud via some user interface, some query interface. So in some cases, we may not need to store daily weight of a 20-year-old, right? But for a 70-year-old, it could be different, because what happens, 20-year-old will have a huge meal, and the next day he or she might put on 3 pounds, but it won't really tax the heart. But if you're 70 and if you put on these pounds, just overnight 3 pounds, that's not good, right? So in other cases, the data may have to be deleted to preserve privacy. And here's a challenge, because when data is deleted, how do you know the data is deleted? So you need accountability policies, so audit policies, right? So it's not like you store your jewelry in the bank, and then when you remove the jewelry is gone. But in data, you remove the data, delete the data, could be still there. We don't know. So we have to make sure that the data is removed, deleted. We envision that the data sharing and analytics will be carried out based on these services, and based on different scenarios. Some data could be sent without modification. Some data you may want to perturb. Some data you might want to encrypt, right? So a number of ways to mask the data. So again, the challenge here is coming up with appropriate policies, then a specification language, and then enforcement algorithms. Okay, so next topic is, how do you apply data science for cybersecurity applications like malware analysis, intrusion detection, and so on? So we've done this similar work for a long time, right? 20, 30, over 25 years. We use past data to build a classification model, predict the labels of future instances. So we know what the data model, the model is built based on, supervised means labeled data, and then we predict the labels for future instances. And this helps with decision making. So you can say, what's the challenge? The challenge is massive amounts of data, big data stream classification. So data streams, continuous flow of data, very common in our connected digital world, massive amounts of data. So because when we talk about continuous data, the concepts are changing, right? So today it's by Microsoft, tomorrow by Apple, next day by Facebook, following day Google and Amazon and so on. Or today it could be one kind of malware, next week it's going to be some other kind of malware, and so on, right? So concepts are changing. So lots of data coming in streams. So we have we build a classification model, not one model, we build an ensemble of models, a collection of models, and some models could be outdated. So back in the old days, we only built one model and we didn't know how to do real-time data mining like 25 years ago. But now we build a collection of models, ensemble, and these models talk to each other. And if they find that some models are outdated, like for instance, once upon a time when I started my career 40 years ago, there was this company called Control Data Corporation. It was the #3 largest computer company after IBM and DEC. And so if today we say, so back in the old days, if there had been a model that say buy control data, today it's worthless because it's of no use because there's no such company. Similarly, DEC, there is no DEC, right? They have all been sold or merged or whatever, right? So the models are changing, right? Concepts are changing, so the models will have to change. And so the outdated models are thrown away and the more modern models are incorporated. So models are being updated. When the test data, so we train, test data comes in, the benign traffic goes to a server, and then attack traffic we quarantine. And so the expert, there could be a human in the loop, but in our algorithms, we come up with a collection of algorithms, various types of algorithms where the model updates. The models are sort of voting. We use a voting procedure between the models, and then they throw away the model that is that is outdated. Okay, so that's what we have done. And we have applied this to insider threat detection. Very briefly, insider threat, right, requires anomalies, rare anomalies in contexts where evolving behaviors tend to mask such anomalies. So these are really bad people pretending to be good people in a company. And so it doesn't have to be humans. These are the people who carry espionage against a country. It could also be malicious processes, pretending to be good processes. So we have designed and developed an ensemble-based tree mining algorithm, right, collection of models based on, we have supervised learning and unsupervised learning, both. Supervised learning, we have used support vector machine and one class support vector machine. One class meaning that the data is skewed, right? If most of the thread data is really small and non-thread data is really large, so it's skewed. So we just use the one class, right? So, and then we have also developed unsupervised algorithms, graph-based anomaly, graph-based structures. In unsupervised learning, because there's so much of data that's being collected for the model, we use compression to model common behavior sequences. This results in classifier exhibiting substantial increase in classification accuracy, and ensemble of classifiers allows the unsupervised approach to outperform traditional. So anyway, that's the gist of insider threat. So this is our architecture. So there are various system calls. You take information from iChunks, right, and then develop an ensemble of models. So as a chunk comes, you extract features. That's the challenge. What are the features you extract? And then you have a model, build a model, and the next chunk comes in, extract the features and so on. So collection of models, then you throw away the models, the model update, right? That's no longer valid. And we use graph-based anomaly detection, one class support vector machines or support vector machine, learning algorithms, and we can apply a combination of combination of algorithms to develop the models. And then we have an ensemble of models. The models are getting updated. When the I+1 chunk arrives, we extract the features and then apply this model, and then we say, is it an anomaly or not? Okay, so that's our work for data science for cybersecurity. In fact, we have written a number of books. The first one was data mining for malware, data mining tools for malware detection. We had collection of tools for email worm detection, for botnet detection, for malicious executables, and so on. And then more recently, we wrote big data analytics with applications in insider threats. So we used some of this work in our more recent book. And right now we are just about to publish a book on secure data science, integrating cybersecurity and data science. Okay, so securing data science, what happens if the data science machine learning techniques are attacked? What do we mean? We develop a model, right? Our models and data to train. Adversary is watching. What's the data we are using? What's the model that we are developing? It's trying to poison our data. It's also trying to thwart our model. So adversary modifies data to defeat the learning algorithms. So it's going to try and defeat the algorithms we are learning. And that's adversarial learning. Adversary is trying to learn. So we've got to understand the adversarial learning. It's not concept drift. It's not online learning. Adversary adapts to avoid being detected. It could happen during training time, during poison time, during test time, modifying features when data mining is deployed. So essentially what's happening is that adversary is learning what we are trying to do and trying to thwart us. We've got to be one step ahead of or several steps ahead of the adversary. So look what happens. This is the support vector machine boundary line. The red squares are bad instances. The blue circles are good instances. So adversary is learned where we are, our model. It's trying to push the bad instances. See what happens. Now we have 1, 2, 3, 4, 5 of these red squares are pretending to be good instances. And so we are going to have what? False negatives. And that's bad. So we've got to learn what the adversary is doing and try to manipulate this line. And that's exactly what we are trying to do. But before that, we've got to study the types of attacks, right? We have looked at 2 classes of attacks. Now, you can say there could be so many, there could be hundreds of classes of attacks, and you are only looking at 2. So what I'm saying is something better than nothing, right? At this time. So we have free range attacks. Adversary can move the malicious data anywhere between the ranges, right? And in our paper, we talk about exactly where to place, where the adversary can place the malicious data. The other model, we have also another model in the paper, and that's the targeted attack, where adversary can move the malicious data closer to a target point. So look what happens. This is the support vector machine. The red squares are bad, crosses are bad instances. The green circle are good instances. And so you can see by having the support vector machine boundary here. So the dash line, black dash line, is a support vector machine classification boundary, right? By having, if you have the boundary here, some of the red crosses, bad instances are missed, right? Because they are going into the green circles. Green circles are good instances. So what do? We play these games and we try to learn what the adversary is doing. And then we try to move this line here, the blue line. The blue line is the adversarial support vector machine classification boundary, right? That's the modified line. So by moving it here, some of the red crosses, not all, they are caught, right? So some of the bad instances are caught, and we elaborate this here, right? So again, test time, deployment time attacks, attacker can modify, what's the type of attack? X to X prime, modify packet length by, you can add dummy bytes, add good words, I'm just looking at the time, add good words to spam email, add noise to an image, right? This is second, okay, noise to an image, and so on. Okay, so now you can see by moving the adversarial line, right, some of the red crosses are being caught as the bad instances, which is otherwise we would have false negatives, right? Now you can ask the question, why not move this blue line right here? If you move it right here, then all the bad instances could be caught. But remember, if you move the line here, then the green circles would be classified as bad instances, whereas while they are good instances. So we are going to get a lot of false positives. So we don't want false positives and we don't want false negatives. Okay, so that's the whole idea of our research. Okay, so this is one of the early papers we published in this top tier data science conference, ACM KDD. And right, and so when we published our initial work, there was hardly any work at the time. We were one of the, I would say, one of the pioneers with that work, especially my colleague, Dr. Murad Kantajulu. He sort of, pioneered this aspect of research. And here, this work actually, our work on classification was my colleague, Dr. Latifa Khan. He really led the team, and we also collaborated with this famous Professor Jay Rehan from Urbana-Champaign. Okay, so now I just want to, okay, so that's finished this topic. Then there's this whole other area called trustworthy machine learning. So while it's useful to figure out what the adversary is doing and so on, another piece of research, and that's sort of more recent, is how do you trust these machine learning algorithms, right? So computations over big data may require massive computational resources, and organizations, automobile companies may use third-party services to outsource some computations. So whenever we use a third-party service, okay, it's a problem because we don't know. There could be untrusted servers, right? There could be man-in-the-middle attacks and so many threats from adversaries. So we are conducting research to use to do some of this processing in hardware. So research in secure encrypted stream data processing with trustworthy analytics using advancements in embedded hardware technology, Intel SGX, to support trusted execution environments. Also formal methods for machine. So that's, I'll show you in a minute. Another area that is really getting some prominence recently, applying formal methods for machine learning, right? Coming up with appropriate logics for specification, for deep learning, and the verification of the machine learning algorithms, right? So what we are trying to say is the specifications, remember, formal methods have been used for hardware verification and so on, verification of programs, but what about verification of machine learning algorithms, right? So what we are trying to do is trying to come up with the specifications and then make sure the implementation software meets the specifications. Okay, so this is the very briefly the Intel's SGX platform. So you have the application memory, SGX library, the wrappers and encrypted codes. The gist of the approach is that we execute the machine learning algorithms in this SGX enclave memory, secure location. So that's sort of tamper-proof. And so those machine learning algorithms cannot be attacked if they are executed in those, if they are executing in those, in the tamper-proof regions in the SGX enclave memory. That's the whole idea. And we have written a number of papers on this topic. Okay, so now we are into about 20 minutes. I've got another probably 25 minutes left. So the second part is security and privacy for Internet of Things, right? In particular, Internet of Transportation and critical infrastructures. So whenever we talk about, recently I gave a talk at the IEEE Smart World Conference and about smart cities. So you have, is there going to be a smart universe? So the basic is the Internet of Things. You have Internet of Medical Things, Internet of Financial Things, Internet of Transportation, Internet of Manufacturing. And then you go beyond an Internet of smart cities and Internet of sort of get the smart world and maybe even, who knows, smart universe. So we are looking at one aspect, right? Transportation and infrastructures. So IoT, right? When you look at it here, your coffee is, coffee maker is connected to your television, to your clock, to your Amazon purchases, to your cell phone, to your or iPhone, to your refrigerator. And so everything is connected. They're all communicating through sensors. Right. So similarly, Internet of Transportation, cars are connected to trucks, connected to trains, and connected to roadworks, right? They're all connected. So what's Internet of Transportation? It's IoT, major implications in the transportation industry. AVs, autonomous vehicles, they improve day-to-day lives, delivering packages, improving traffic. And in US, trucks alone carry an estimated 63.3% freight of goods. Autonomous vehicles are not limited to ground, right? Ground vehicles. You can have air vehicles, sea vehicles, ships and submarines, aerial vehicles like drones and airplanes. And so levels of automation for AVs, they range from 0 to 5. Ground, I think they've got lower automation, surprising, level 2. And aerial have high automation, level 4. Companies are investing heavily. GM spent about, what, $728 million in 2008, $1 billion 2019, and I believe more in 2020. I need to get the numbers. While there's great potential in AVs and the improvements it can do to the transportation industry, of course, security and privacy is a major challenge. So what are some of the security challenges? AVs evaluate their environment using a variety of sensors, camera, GPS, inertial measurement units, and so on, LIDAR, radar, ultrasonic sensors. And the previous research has shown that sensors are susceptible to malicious tampering, IMUs are susceptible to sound waves, and GPS receptors are susceptible to spoofing signals. and vehicles must verify the veracity of sensor signals. So what are the challenges? They are sensor-based, right? So AVs rely on sensors to evaluate and interact with their environment, whereas network traffic is just bits and zeros and ones. Sensors are susceptible to GPS spoofing, as we have said here, and transduction attacks that manipulate environmental physical signals, visual sound, and so on. So that's the inherited issues. Then what are some of the defenses? Classical computing, right? Security like memory protection, cryptography may be necessary, but not sufficient because you've got so much more complex data and different types of attacks. And then there's no verification, right? So due to real-time constraints, AVs have to trust upon and act upon sensor data without any form of verification. So there's a potential for all these attacks. So what sort of verification do we need? Okay, that's a challenge. So we came up with a physics-based anomaly detector. What do we mean by that? We built a reference monitor, the security critical component that's controlling all types of accesses. And so we modeled all the physical properties, right? So my colleague, Dr. Cardenas, is a control systems engineer, so he's very well familiar with modeling the cyber physical systems. So our algorithm, so we developed a physics-based anomaly detection for ground and aerial AVs. So algorithm has three parts. We build a model offline, right, of the AV's physical invariance, implementing an online tool, expected and observed behavior to detect anomalies and raise an alarm if significant residual difference exists between executions. So you could ask the question, what's the big deal? Okay, the big deal is a few things. One is that modeling the behavior, physics-based modeling, you've got to, because if you are not modeling correctly, then you can have the best attack detection algorithms. It's not going to work. You need to come up with the attacks, understand the attacks, and understand the models. Okay, so for example, K here is the state, YK input sensor measurements, and UK is commands to rotors. You have the X, Y, and Z axis moments of inertia, M is mass of vehicles, and drag factor, thrust factor, and so on. So the AV's invariants are calculated using well-known nonlinear models for aerial and ground vehicles. Accelerometer, gyroscope, and magnetometer sensor data on the X, Y, and Z axis. Z axis is used for aerial vehicle. Vehicle position and steering angle is used for the ground vehicle. Online stage, we have an extended Kalman filter. It's used to predict AV's physical behavior, estimating unknown parameters from noisy sensor inputs, right? And then the algorithm is divided into two sections, one that predicts and corrects the estimation before it is compared against the sensor data. Okay, so that's the online. We use extended Kalman filter. At this time, no sophisticated machine learning techniques yet. Okay, and Kalman filter has been around for about what? Years and years. Electrical engineers, control systems engineers have used it. For anomaly detection, we use the QUSUM. It's a statistical algorithm, is then used to detect persistent attacks, and alarm is raised if the residual difference is larger than a predefined threshold. That's our detailed design. Okay, and our paper describes the details. The physical implementation, remember, we didn't do it for ships, just for sea vehicles, just the aerial. For aerial, we use the drones. Ready to fly RTF drone, it's a controller PX4, flight controller focused on, remember for drones, aerial, GPS spoofing is gyroscope attacks, GPS attacks are detected for GPS spoofing 0.2 and gyroscope attacks are after 1.5 seconds and overhead is about 5.4%. Ground vehicles, right, that's here, the cars, custom built on top of Traxxas Ford Fiesta, Rally Chassis controller, ROS Kinetic Game focused on detecting visual attacks on the camera, attacks detected after 0.1 seconds, overhead introduced is about 2.25%. And each threshold produces probability of false alarms of about 2%. Okay, so we have false alarms, which is still quite high actually. Okay, so that's our security. Privacy, we haven't really done much work on privacy, but again, it's important because beyond the security of vehicles, transportation sector could greatly benefit from a supporting infrastructure, allows communication between vehicles, motion sensors on lamppost, surveillance cameras to help identify traffic jams, reroute the vehicles, increase vehicle safety, and so on. Okay, so without a doubt, the machine learning algorithms and so on are being used extensively in transportation systems to reduce the number of accidents, again, reroute vehicles, to identify traffic jams, give the best information to passengers and drivers. But from a user's perspective, privacy concerns arise from all the information needed by such a system, because more data you collect, right, there's a more chance to violate privacy. So I may not want my driving patterns to be disclosed. No, I may be smoking in my car, which I don't smoke, by the way. I may be smoking in my car and I don't want other people to take photos and send it all over the place. Or I may be in a particular location and I may not want anyone to know where I am, right? So these are some of the privacy concerns. So legislators, engineers, and scientists should keep privacy in mind as we make advances in IoT, right? This will aid at improving the public perception, reduce hesitation from consumers, and increasing the adoption rate. Because the more, if people have more confidence, there's some level of privacy, then they will use these technologies, right? So that's something, we are beginning to think about for transportation systems. Now, so we finished part 1, right, which is various topics in big data security and privacy. And part 2 is Internet of Transportation and Infrastructures. And part 3 is focusing on applying part 1 to part 2. And that is applications of SecAI for Internet of Transportation and Infrastructure. SecAI means security and AI. Okay, so we talked about a number of topics, right? Data science for cybersecurity, and then securing the machine learning techniques, right? So what can we do here? Data science for transportation security. So Internet of Transportation systems subject to attacks. We said gyroscope attacks, GPS spoofing. It's just like any other cyber physical system. And they're streaming data, right? Data is coming in streams because sensor data continuously arriving, right? Including autonomous and future we could have driverless vehicles. So as transportation systems go electric, we will need energy conservation. Threats to the security of systems could cause massive damage, accidents, loss of lives, stranded on lonely highways because we would have lost the energy. Data science, machine learning are being applied to analyze the data. That's our current research. And so the question is, can stream data analytics, remember what I mentioned earlier on, can we apply this to, say, financial data, right? Financial data and that we have applied for financial data and telecom data, network data, security data, and so on. Can we apply those techniques for transportation systems, okay, or transportation data? And what's the type of data? Sensor data. So we really have to understand the structure, the complex transportation data, and adapt the stream analytics and apply them on massive amounts of heterogeneous sensor data. So we really have to understand what sensor data. We understand financial data, network data as bits and bytes and so on. So what does a sensor data look like? And how is it represented? And is it really heterogeneous? So we need to really understand the complex sensor data and the different types of sensor data, and then come up with appropriate data science techniques to detect anomalies in the sensor data. Because remember, one thing I wanted to mention is that, I forgot to mention earlier, if these transportation systems, right, if they are attacked, imagine what could happen, right? It could go, everything could be crazy because the trains will collide into cars, will collide into roadworks and the trucks, and everything could be a big, big, big mess. And that's why we really need to address the security. Okay, so next we talked about adversarial machine learning, right? So what we are saying here is what happens if the machine learning techniques are attacked. Without a doubt, as we said, transportation systems, they are using machine learning more and more, because machine learning is applied almost everywhere now. Healthcare, finance, retail, manufacturing, marketing, right? And medicine, coming up with pharmaceutical companies. Everybody is using machine learning, and similarly transportation systems, IoT, smart world, smart cities, because machine learning is showing promise, right? Providing some intelligent aspects. So for the transportation systems, optimum directions, driving without a human in the loop, and so on. But whenever you are using machine learning techniques could be attacked. Adversary is trying to learn our model for machine learning and what data we are using to train the models, and adversary is trying to thwart the model. Adversary will attempt to thwart the vehicle's learning process. We've got to be several times ahead of the adversary. So our learning algorithms have to adapt to thwart the adversary's actions. So it becomes game playing, right? Between the adversary and us, what sort of game? Is it zero-sum game? Is it Bayesian? Is it, let's see, Stackelberg game? So we really need to understand that the complexity of the data. What does the data look like? And research is only beginning on this topic. Then we talked about policy-aware, privacy-based, privacy-aware, policy-based data management framework. Remember, with a cell phone or smartphone, we talked about data collection, collecting social media data, healthcare data, and so on for quantified self. So I have a similar picture. We haven't started work on this. We have this car, and inside the car, we have some kind of a gadget, just like a cell phone. So we collect data, store data, analyze data, share data. There's radar, GPS, cameras, LIDAR, ultrasonic sensors, some of the data in cloud storage, encrypted, some in cloud-based or edge. For transportation, Internet of Transportation, because it's very time-consuming to go to the cloud and back. So we may want to have storage devices, little mini clouds as the edge, right next to the transportation system, next to the hubs, right? So edge and cloud for encrypted data, anonymized services, and so on. So that's the direction I think we will be going for privacy-aware, policy-based data management framework. So our data collection, transportation data collection based on policies, storage, access policies, analytics based on policies, similarly sharing based on policies. Okay, so part 4 is role of the cloud. So what do we mean by cloud, right? Because you can see throughout the presentation I've given, cloud plays a major role, because when we talk about the privacy-aware policy-based framework, right, cloud is being used to store all of the cloud and edge being used to store the some of the encrypted data, because lots of data being generated and we can't store them in a car or in our smartphone, iPhone, right? We need backup. So a lot of the data is being backed up, like the iPhone, the Apple cloud, and the Google cloud, and so on. So there is a cloud, but again, whenever we are using cloud, security is of utmost importance. So massive amounts of data collected by the Internet of Transportation, privacy of the individuals have to be protected. As more and more sensor data collected, storage of the AVs will not be sufficient to store all the data. We envision encrypted cloud storage component where all the data and all less frequently accessed data pushed to the cloud. Again, based on the access control policies, local apps running on AVs will be given access to some of the collected data. When needed, these AVs will be allowed to access some of the encrypted data through these cloud services, through some simple query interface. We envision that much of the data sharing and analytics will be carried out using these various services running in the cloud. And information sharing in the clouds is not only between the AVs, the autonomous vehicles, lots of information sharing, right, between the trucks and the cars and the roadworks and so on. But we also have sharing among the agencies, the local agencies, your driver department of motor vehicles, and the local agencies, the state agencies, they all have to share data. So all of this data could be shared through the cloud. And I'll give you an example. That means the cloud must be secure, right? We need a secure cloud to carry out these security functions, right? Secure information sharing, secure storage, secure access, and so on. So we have developed a assured cloud framework, right? Funded by the Air Force. We have developed a layered framework. So cloud framework typically could be a layered architecture, secure virtual monitor for virtual network monitors. And we really haven't done much here on this, but we've done quite a bit of work on securing virtual machine monitors like VMware and Zen and so on. and cloud storage manager, Hadoop, MapReduce, Spark. So we have developed technologies to secure Hadoop and secure MapReduce. Cloud data manager is to store all of the data in the cloud securely. And then the user interface applications. Then we have policy specification, policies, quality of service, monitoring the cloud for attacks and risks and costs, because cloud's very expensive, right, to build the cloud and store the data and so on. And so we may have to encrypt the data, mask the data. And the whole challenge is for us is, what are the risks? If we are not going to have any attacks, then we don't have to worry as much. But unfortunately, we live in a world where lots of cyber attacks, right? And so if the costs are really, really tiny, then it's not that much of a problem. Then we can take all the precautions. But if it's really costly, if security comes at a huge cost, then it sort of becomes a dynamic programming problem between the risk and cost and the utility of the data. So we have worked on the main layered architecture, as well as some of the additions like policies and quality of service and cloud monitors, and applying dynamic programming for risk versus cost and so on. And the right-hand side is the actual technology. So we have Zen Linux virtual machine. We have the Hadoop MapReduce storage, secure. We looked at secure Zen and secure Hive Sparkle query, and policy sign XACML, RDF, semantic web languages. And the ones in pink are still sort of ongoing and still need more work. Ones in blue are sort of parts we completed. The monitoring part and resource allocation and the policy specification, query processing was really one of my areas. And then, it's a team effort, right? Lots of people worked on this project. So we are assuming the cloud is secure. So using a secure cloud, how can we share data? So we build some of our cloud technologies. This is our cloud, right? So we have, Sparkle query, because remember, we are saying policy sign RDF. So we query the cloud in Sparkle. Sparkle is a semantic web query language. And this is sort of what the processing we do for manipulating the data and processing the data, processing queries. But the whole idea that we have developed, not for transportation, for general applications. So we have 3 agencies. So this joint work actually between UT Dallas, King's College, University of London, University of Insubria in Italy, right? We did this work for the Air Force. And so US Air Force, we were funded by the Air Force in Washington. US Air Force also has a branch in Europe, in London, which funds research in the EMEA region. And they also have something in Asia Pac, in South America, right? So we have multiple agencies. So, or it could be between vehicles, autonomous vehicle 1, 2, and 3, or between multiple agencies, between vehicles and agencies. So one thing though, when you are sharing data between vehicles, you may not want to go through a cloud or sometimes you might want to, because it's very, very time consuming, right? So, but between agencies, you may want to go through a cloud. So or edge, what happens is we store all the policies and data in the cloud, right? And whenever they want to share information. So it's not like the policies cannot be toy policies, like Tom tells Jane, I will tell you a secret, provided you don't tell that secret to Robert. Okay, so those types of toy policies don't work. There are realistic policies about information sharing, and that's what we've got to specify and enforce these policies. So the data and the policies could be anywhere in the cloud. And so when agency 1 talks to agency 2, and according to the policies, then it goes into here, looks at the policies, and then gets the information it wants or shares the information with agency 2 or agency 3, right? So again, when we have communication between the vehicles, it may be too time consuming because it all has to be done in real-time fashion. So this is one approach for information sharing. So again, cloud plays, the point I want to make is that the cloud plays a very important role in security and integrating security and AI with respect to privacy, encrypted data stream, data science for cybersecurity, and adversarial machine learning. So Internet of Transportation Systems, cloud plays a major role. Okay, So, and again, we need the cloud to be smart, right? Smart cloud meaning it's not only secure, but we also want the cloud itself to use machine learning techniques. That's another approach, another aspect. Cloud itself to use machine learning techniques, so we have an intelligent cloud that can make intelligent decisions. Where to send the data, which part of the cloud to store the data. Should we use a public data? How can we separate into public clouds and private clouds? How do we store the data? Some data goes into the public cloud, some data into the private cloud. All of these decisions have to be made by the cloud. So the cloud is essentially a smart cloud, which is very relevant to this conference. My last chart, right? Developments in integrating, cybersecurity, AI, data science exploding. Applications of AI for security inside a threat, security for AI, adversarial machine learning, developments in privacy-aware healthcare and managing one's life's activities, that's privacy-aware quantified self. At the same time, with the development of the Internet of Things, including Internet of Transportation Systems and Infrastructures, security and privacy solutions are being developed, mainly physics-based solutions, right? Driverless cars become a reality. More and more of the AVs will use AI ML techniques. How can we develop AI solutions for detecting malware in AV systems, and how can adversarial machine learning work in AV systems? Can we develop a privacy-aware policy-based data management framework for Internet of Transportation and Infrastructures? That's the example I had with the car, picture of the car. And of course, is it possible to perform trustworthy machine learning, right? Efficiently, that means, can we bring the Intel SGX platform, right? How can we use that? And what about formal methods for IoT security, right? We have to sort of focus on formal methods first for machine learning, and then talk about IoT security. And what is the role of the cloud in this whole space? So what I have mentioned today, I've talked about several topics, a bit of everything, some that we have already done a lot of work and some future work. Numerous opportunities exist for substantial research and development. What I have discussed today, right, that's enough for 10 PhD theses, I think. Okay, so lots of opportunities. And that's what I wanted to provide for you all, a flavor of sort of the research and all the opportunities in front of us. So I'd like to thank my colleagues, as I said, Professors Cardenas, Kantajalu, Khan, and our joint PhD student, Dr. Raul Quinones, and our project coordinator, Ms. Rhonda Walls. Okay, so now I'm going to stop sharing, and I will be at the conference, right? It's going to be 2 hours from now. And so the conference chairs could play this presentation, and then I will be there to answer questions. So if they want me to give this presentation live, I will be happy to give this presentation. And so again, thank you very much for inviting me. And I'm really looking forward to participating in this conference and answering questions, and thank the organizers of the conference for putting together this great conference and lots of very interesting papers. And again, this topic that we have discussed, I've discussed the whole topic, smart cloud. It's going to be a huge area for us, regardless of whether we are talking about Internet of Things, Internet of Transportation, Internet of Medical Things, Internet of Manufacturing, right? And when we bring AI and security and privacy, again, they all have to be integrated in order to develop this smart cloud. Okay, so I'm going to stop there for now. And I think I've taken about 50 minutes actually. And so we will still have time, I believe, for questions. And again, thank you very much.